Hello everyone. Um, I'm Yuvraj, a research scholar from IIT Madras. Welcome to this Spark workshop on use of recycled aggregate in concrete. We appreciate everyone joining from different places, both at Zoom as well as in the YouTube. So we will first start with a brief introduction about the workshop as well as about Spark by Professor Manu Sandhanam from IIT Madras. Over to you, sir.
Well, good afternoon to all of those in India, and good late morning to those of you in South Africa. Welcome to this workshop, which has been jointly organized by the students of IIT Madras, along with the students from University of Cape Town and University of Witwatersrand. Of course, the program between these three universities has been going on for quite some time. We've been collaborating since 2004, when we started on our first project together. The current project, of course, deals specifically with recycled concrete. And I'll just take you through briefly the aspects that we are trying to understand in this joint project together, and how this workshop basically is one of our attempts to bring together the knowledge base that is there in both these countries with respect to the research that has been conducted. And I'll then introduce you to the kind of topics that we're going to be discussing in today's workshop. So let me share my screen and talk a little bit about. Yuvraj, can you let me share my screen? Oh, sorry. Yuvraj, I'm unable to share my screen. Can you enable screen sharing?
You have to be made co-host, Manu.
I think I'm already co-host. Yeah?
You should be able to share.
Sir, you can try.
Yeah, now I can share. Yes. Sure. Okay, so the Spark project between IIT Madras, University of Cape Town, University of Witwatersrand is titled Towards Durability Specifications with Recycled Concrete Aggregate. What we want to do with this project is answer these key questions as to how the current performance approaches should be modified when recycled concrete aggregates are used in place of natural aggregate. As you know, there is a lot of emphasis these days on durability design and trying to address durability design with the help of several accelerated test methods. Now, what happens is when we start using alternative materials instead of the regular conventional materials, the properties of the concrete are bound to get affected. What we need to understand is whether by the use of recycled aggregate, we are capable of using the currently available approaches of durability design, or should we make some changes to that? Then, of course, going in the same line, is there a different set of limiting values that need to be applied for durability parameters when recycled concrete aggregates are used? So that's the other aspect that we are trying to address in the deliberations that will arise out of this joint research project. The tasks that we have set out within this project include strategies for removing mortar from aggregate, that is to enable obtaining pristine aggregate from recycled or demolished concrete sources. Second is to generate database on strength and durability properties of concrete with coarse aggregate, and review of existing provisions with recycled aggregates in both the countries, that is India and South Africa. We are also looking at research studies that are being done in both these universities, or all three of the universities, dealing with the properties of concrete with recycled aggregate that is either in the as collected form or processed form, and comparison with the local natural aggregate. And a most important aspect of the research program that we are setting out together on is to assess the life cycle using suitable frameworks that are available today, because ultimately the usage of recycled concrete as aggregate would depend a lot on what the overall life cycle is and life cycle cost is. And that's something that is also key to the approach that we are actually following in this joint project. What we hope to deliver from this project are guidelines for durability design with recycled aggregate concrete. And of course, there will be a set of workshops that we'll be conducting. The first workshop was conducted on Jan 18, 2020, earlier this year in Chennai, where Professor Mark Alexander from University of Cape Town also took part. We'll also be recording lectures for a video course that will be offered in the near future. And of course, we'll also have a monograph that will come out at the end of this project to ensure that we are able to capture all the essence of what we have actually learned through the course of this project in a written document. Right. So what do we look forward to in today's workshop? We have organized the sessions in such a way that our students who are working on either side of the ocean will talk about first the understanding of logistics and impact of construction and demolition waste recycling, exploring techniques for processing recycled aggregate concrete, understanding the influence of recycled materials in terms of fine aggregates that are obtained from different sources like demolished concrete and masonry rubble, and a very interesting study on aggregates obtained from alkali silica reaction damaged concrete also. So the discussions today will involve presentations primarily from the students who are actually working. So this workshop, as you're aware, is entirely organized by the student group of researchers on both sides. Often it turns out that most of us faculty present the work which has been done by our students and get the good name for it, whereas the actual work has been done by the students who are putting in their hard work and dedication so that we get to project all the good results. But this time, we have asked the students to actually do the presentations themselves. The faculty will only moderate the sessions, and the presentations by students will be made directly by the students, and there will be, of course, a round of discussions towards the end. So with me today are also my faculty colleagues from IIT Madras, Professor Ravindra Gettu and Professor Surinder Singh. And from the South African side, we have Professor Yunus Balam, Professor Mark Alexander, and Professor Hans Boyshausen. Of course, along with the entire research team from all of these three universities. So I hope that you all have very productive 3 hours ahead of you. And I hope that there's a good way forward for us towards the end when we deliberate on the topics that we discuss in the workshop. I'd also like to share a couple of slides about a program that we have currently for you. Just give me a minute. This program is called eGrishma. This has been started by IIT Madras. It's a virtual global research internship in engineering, science, humanities, and management offered by IIT Madras. Of course, all of you are aware of IITM as being one of the top institutions in India. We have been ranked #1 for the last 5 years amongst the Indian universities. This is a unique program which is being offered for final year undergraduate and postgraduate students. It's a 3-month online research internship, and there's a screening process through which selections will be made. There'll be an opportunity to work with the IITM faculty in this program. And of course, you can get more details about this program from this website address that is being shared with you here, oir.iitm.ac.in/GREISHMA. Okay, and there are several topics which have been outlined here. You can, of course, get more details directly from the website. Okay, with that, I'll hand over the organization to Yuvraj. So go ahead, Yuvraj. Thank you.
Thank you, Professor Manu. So with this introduction, we will move to the first session, where we have a couple of interesting presentations. The session will be chaired by Professor Yunus Balam from University of Witwatersrand. Professor Yunus,
Thank you, Yuvraj.
Yeah.
Can you hear me all okay?
Yeah, all okay.
Okay. Thank you very much. Good morning or good afternoon, everybody. And Manu, thank you very much for that introduction. It was most interesting. I'm going to dive straight into the session. There are two presentations in this very first session, and as indicated, this will focus on waste recycling, etc. And the first presentation is environmental performance of construction and demolition waste recycling facilities, and that's going to be presented by Mr. Ram, who's based at IIT Madras. Ram, are you ready?
Yes, Professor.
Okay, I'm going to be quite strict with the 15 minutes. I'll give you, when there's 2 minutes remaining, I'll give you a note, okay? But otherwise, I'll be mute. Thank you very much.
Sure.
Please go ahead.
Okay. Thank you, Professor Balan. Let me share my screen. So I hope you can see my presentation. So the title of my talk is Environmental Performance of C&D Waste Recycling Facilities. So just before my talk, I just want to give a caution note to all the hardcore material researchers, because this talk is entirely on life cycle assessment, and it is not actually a laboratory-based study. So in the next 15 minutes, if you don't hear the words such as mechanical properties or material characterization or recycling technology, please bear with me. So you're not in the wrong workshop, you're in the right track. Just hang on for the next 15 minutes. Yeah. So that's it. The outline of my talk will be, I'll give just a brief overview on the need for research in C&D waste management, that is construction and demolition waste management. Then the challenges with respect to quantification, economic viability, and other challenges. Then I'll give the rationale for the need of life cycle assessment and the inventory data that we have collected. Then the interpretation of results will be illustrated with a case study in two lenses. That is, the first lens is the comparison of natural aggregates versus recycled aggregates. And the second lens is the landfilling as a practice versus recycling as a practice. Okay. So C&D waste has been a big menace to the environment. So it is a universal problem, and every city in the world is actually choking on construction and demolition waste. So these concrete and masonry debris are being thrown away in all streets in every cities. And the problem is not just limited to resource depletion, but it is also the pollution that is associated with it on air, water, and soil, and whatnot. So whatever the cascading effect of this practices is, for example, in Chennai, these debris has actually choked the stormwater drains that are in the city. And when there was heavy rain, it flooded the entire city. So that's the kind of cascading effect these kind of practices can have if not properly managed. So what we are essentially building is actually garbage mountains of these waste. So what we have is a disposal problem on one hand. On the other hand, we are also actually rapidly developing our cities. So what we need is huge amount of resources to funnel our infrastructure development. And so what we need is aggregate. But then we are again breaking the mountains to get those aggregates. And we know that natural resources are scarce and we have to conserve them. So these are the twin problems of the society. And recycling can be seen as a potential solution that can actually solve both of these twin problems, right? However, there are a lot of knowledge barriers that actually impede the smooth transition towards a recycling society. Okay, so now that we know recycling is a good solution, do we have enough quantity of waste that can be recycled? The literature says yes. The total amount of waste that is being generated in various cities range from 100 kilograms per capita per year in India and Taiwan, all the way up to 800 kilograms per capita per year in Shanghai and Spain. So that's the amount of waste that is getting generated in the world. And we can safely assume that the developing countries, especially the BRICS countries, the waste generation is only going to increase. Okay, so we do have enough amount of waste that is being generated, but are we recycling it? In most of the developing countries, we are not. So, for example, in the Indian scenario, the installed C&D waste recycling capacity is right now just about 2.5 percentage of the total waste generation. That's abysmal. So, why? Why do we don't recycle? Because we can safely assume the technology that is needed for recycling is more similar to a normal crushing facility, right? The answer to that question can be slightly counterintuitive because the cost of recycling is actually higher than the revenue that are generated from operating such a facility. This from my own research I found out, and the data is from the Indian scenario, but I've just converted into US dollars so that everybody can make sense of it. The cost is about $7 US. However, the revenue that I can generate is only about $4 US. So how will a private entity will actually enter this such a enterprise? So why the cost is so high? Because we tend to think recycling should be cheaper because we get the raw material that is needed for the operation of the facility at no cost, right? The waste is being thrown away, you just have to collect it. However, the collection cost itself is more than 50% of the entire cost of this operating a recycling facility. So why is it that the collection becomes so big cost factor? If you take a natural phase aggregate facility, the entire raw material feed is available at a single place, like quarry or a mountain. However, in the case of a recycling facility, it needs to fetch its raw material from widely distributed points. For example, on the screen, what you see is actually the Chennai city map, wherein in every year, about 5,000 to 8,000 construction or demolition activities happen in different locations. And all these waste have to be collected and accumulated at a single point so that economies of scale can benefit a recycling facility. Right? So that is why recycling is economically not viable. Okay, so now we can now understand why it's not economically viable and why there is so much cost. But then it now brings to another problem saying, okay, if it is higher, it is of higher cost, which means huge amount of resources are being consumed for it. And if higher amount of resources are being consumed, that actually leads to a normal conclusion that is it really environmentally beneficial? Because we are putting more resources on it, right? So that's the question that we are going to answer through our life cycle assessment study. So what we have done, we have actually defined our system boundaries on three processes or facilities. So system boundary for the natural aggregate production, system boundary for the recycle aggregate production, and for C&D waste landfilling practice. So on the system boundary, we have collected data primarily through in-person interviews, observations, and questionnaire. So we have also used the secondary data from the Eco-Invent database, which is an European database, and the Semaphore software to actually convert the inventory data into impact assessment. The data is collected for a period of 1 year in each of those facilities, say natural aggregate facilities, recycle aggregate facilities, and the landfills. So the data that we have collected from each of these facilities is the kind of resources that are consumed in each of those facilities. For example, in quarry, we have collected all the resources consumed and we have quantified them. Similarly, at the crushing facility of the natural aggregate, we have taken 3 different facilities and we have quantified the data that are resources consumed in each of the unit processes involved in those facilities. Similarly, for the recycle aggregate, we have taken 2 different facilities of 2 different capacities in different locations. We also quantified the resources consumed in each of the unit processes. So that's the data that we are looking at. Okay, so at the inventory, the diesel, for example, in the natural aggregate facility, the diesel consumption is roughly about 2 liters for every ton of production. Electricity is about 3 to 4 kilowatt hour of every ton production, and water is about 4 to 6 liters of every ton production. If we compare it with the literature from across the world, while diesel consumption is slightly on the higher side in India, the electricity is roughly comparable across the world. For example, it is comparable with Brazil, Italy, and South Africa. So when we go to the recycle aggregate facility, again, it is again almost similar to the natural aggregate facility because the technology is not really very different from the natural aggregate crushing facilities. So the diesel consumption is again about 2 liters for every ton of production, and electricity varies from 1.5 to 3 kilowatt hour of production, and the water varies from 6 to 8 liters of production. Again, if we compare it with the literature across the world, we find that India is not really off the picture. It is not being that inefficient. It's almost comparable all over the world. So now that we have the inventory ready, so to illustrate the application of LCA results, we have taken the Chennai as a case, and we have taken 4 scenarios. The first scenario is just plain landfilling, that is L1. The second scenario is L2, where the present landfill is depleted and we are forced to look out for a future landfill that is far away from the city. So the transportation distance increases. The third scenario is R1, is just recycling the entire amount of waste that is getting generated. And the fourth is R2, that is again recycling, but with an extra network of transfer stations to aid the logistic network. So another factor that we are going to add in this scenario is the avoided burdens of natural aggregate production. So what is this? So for example, if you produce, say 1 ton of recycled aggregate, it will automatically eliminate the need to produce an equal amount of 1 ton of natural aggregate, right? So thereby, the emissions that are produced from producing 1 ton of natural aggregate is eliminated. So thus, we consider the avoided burdens of NA production, as well as because we have recycled the waste that is not being dumped in the landfills, we are also including the avoided burdens associated with landfilling an equivalent amount of waste. So thus, these 2 avoided burdens will actually have a bigger say in whether answering the question of is recycling environmentally sustainable or not, right? So is the consideration of avoided burdens is new? No, it is very popular in the literature. For example, the same device literature, you can see different kinds of materials and their consideration of environmental traits obtained has been considered. So in this study, we have only considered the avoided burdens of aggregation and the landfill avoidance. So other metals, wood, plastics, cardboard, paper recycling, we haven't considered. So that's one of the uniqueness of this study. So based on the inventory, the scenarios that I have discussed, we are actually able to quantify the transportation that are involved and other related data. We have used Impact 2002 plus method to actually map the inventory into environmental impacts. So what it does is, from the inventory data, it is actually mapping the impacts in 15 midpoint indicators, and the 15 midpoint indicators are mapped onto 4 endpoint indicators, which are human health, ecosystem quality, climate change, and resources. So this is the results of our study. So here on the left, you see the 15
2 minutes,
midpoint.
Ram.
Yes, Professor. So on the left, you find the 15 midpoint indicators. What you see is, so recycle aggregate production, there is consistent decrease in the amount of impacts that are generated as compared to natural aggregate. So just to take one category, say global warming, it is measured in kilograms of CO2 equivalents. It is all carbon emissions are mapped onto a single denominator. So natural aggregate is about 12.5 kilograms CO2 equivalents. However, the recycle aggregate only produces 5.5. So that's, we have about 57% reduction. So considering all the midpoint indicators, the overall reduction somewhere about 85%. So these results are anomalous. To just give you an easy comparison, I'm converting it into a single score. So for example, in the natural aggregate, it is about 5 to 6 millipoints. So the millipoint is just the impact caused by one person on the planet. This is based on just normalization. On the other hand, for the recycle aggregate, is just about 3 to 3.5. So you can clearly see the difference between the natural aggregate and recycle aggregate. Thus, there's a benefit. To just give a comparison, 1 kg of steel generates somewhere about 86 millipound. So that's the difference between steel and aggregate manufacture. So to move more about, there are 4 endpoint indicators. If we compare landfilling, these generate environmental impacts on the positive side. However, if we compare recycling, these are actually producing environmental benefits. So if you have a negative number, it is actually denoting that there are environmental benefits from that activity, that is recycling. So where are these benefits are coming from? These are benefits are predominantly coming from the avoided burden of natural aggregate production and avoided burden of landfilling. So we have also considered a sensitivity analysis wherein we have varied various parameters, including the transportation distances to about 400%, the transportation distance from quarry to a crushing unit. The diesel electricity consumptions have been varied up till 475%, and still the results holds good. Even the transportation distance to landfill have been varied, and the results were absolutely same. That recycling produces benefits. So just to give a number, if Chennai has practiced recycling, it would have actually prevented about 2,000 tons of CO2 equivalent emissions in just 1 year, and it gets accumulated every year. So concluding comments, recycled aggregates lead to 85% reduction in the overall impacts as compared to natural aggregates. Recycling scenarios show environmental benefits in all 15 categories, and a reduction of 300% at least in impacts is observed in recycling scenarios as compared to landfilling scenarios. So for detailed data and reading, you can follow the journal that we have published in a production journal, and as well as the chapter. I would like to acknowledge Kishore Kumar, who is an MS scholar, who has been a colleague, who has worked along with me in this research, and also the funding agencies, including MHRD, UKC, and the DST in the Carry project. Thank you.
Thank you very much for that, Ram. Certainly a most interesting presentation. I particularly like the fact that you've started to establish a framework on which these kind of questions can be analyzed, and that was very useful. There have been 2 questions. I think I'm going to read both questions, and I'm going to ask you to respond to them. The one is, what will be the cost of the recycling process per ton, apart from the aggregate costs? You know, there's just the purely value add cost, if you can think of it like that. And then the second question is the process of recycling of aggregate and recycling of reclaimed asphalt pavement materials the same? Can I say that again? Is the process of recycling of aggregate and recycling of reclaimed asphalt pavement materials, are those two the same? Please go ahead, Ram.
Yes, Professor. So to answer the first question, the cost actually depends entirely on the transportation distance as well as the capex. So to just give indication of the capex costs that are involved, for example, the capex alone can be somewhere about 150 rupees, that is about $2 per ton. And the operation cost can again be another 150 rupees per ton, that is about again $2 per ton. But I am not including the secondary collection or the primary collection in this figure. So which means your about $4 per ton itself will go into capex and opex, and your collection and the land that is involved are not included in it. So that's the kind of unviability that exists in this. So unless there is potential support in terms of regulatory framework or some subsidies, it's going to be really tough for the recycler to operate. Second, as is the process of converting the bigger chunk of concrete or the asphalt using a crusher will be same. However, the application of the recycled aggregate or the recycled asphalt pavement is slightly different depending upon the properties that are associated with it. So it's more of the philosophy might be the same, but the operation will be different in both production as well as the application of it. I'll leave it at that because maybe another professor, Surinder Singh, and other experts in recycled asphalt pavement might be able to elaborate more on that.
Yeah. Yuvraj is the last question. Sorry, Ram.
Yes, Professor.
Sorry, the two last questions quickly.
Yes.
How do we quantify the indirect impact of having efficient recycling process instead of dumping aggregates? Example, water bodies, pollution, etc. I guess that's the question of the framework that you've established. And then the last question, how are you characterizing construction demolition waste for inventory data? What are all the limitations of CIMAPRO with respect to Indian context? I guess that is a far more detailed question than you can answer in this session. And perhaps the questioner should engage differently, but maybe you want to make a comment. Go ahead.
So to answer the first question, if I understand the question correctly, they are essentially asking about the kind of indirect impacts on the water bodies and other, how do we measure it? So as I have explained in my presentation, I have actually used the EcoInvent database to do it because in the Indian scenario, we really do not have such extensive databases that have been developed so far. So that's why I have actually augmented my primary data along with the secondary data from those generic databases. So in the probably that's one of the research areas that people can actually undertake as an industry body or as a researcher, and probably augment the databases with Indian data so that we get a richer description of results. So far what I have done is only predominantly based on European generic databases. So that's again a limitation of this work, but again the philosophy is same. So you might be able to interpret the results in the same philosophy. To answer the second question, it is again more of on the framework, right? So how do we measure the entire data that we have collected? So it is not an easy process. So to actually even estimate the amount of waste that is generated in Chennai city alone, it took more than a year for us, because we had to actually go and get the data from each and every offices, because people do not really store the information on computers. They just store it in hard copies. And if we are lucky, the termites don't eat them, and we get those data in one whole package. Otherwise, then we'll have to go on search about data. So that's one of the toughest tasks in if you are especially doing process-based LCA. So you are actually quantifying each and every processes and the so again, so that is why we have actually taken in terms of the quantity that are generating in India. We have quantified it depending on the each and every truckload that have happened in Chennai city for over a year. We have pulled out the reports from landfills, from corporation offices and various other entities, and that's how we have actually built our primary database. And of course, we have augmented that with secondary database to actually convert the inventory data on the environmental impact. Yes. I hope I just clarified that.
No, as I said, I thought that was going to be a long question to try to answer in this session.
Yes.
But well done, Ram. Thank you very much, and thank you for your presentation.
Thank you all.
I'd like to move on to the next presentation. I've just received a note that says that there are more than 200 people on the YouTube connected on the YouTube. So this obviously is attracting a lot of attention. The next presentation is by Nima Kahabi, who's based at University of Cape Town, and she'll be talking to us about the effect of partial replacement of fine aggregate with recycled concrete and durability properties of concrete. Nima, please go ahead. Are you ready for your presentation?
Yes, Prof.
Please go ahead. Excellent. There we go. Thank you.
Can you see the whole presentation, Prof, or you see?
No, we see your entire. We see the whole presentation. Everything is visible. Well, I can anyway. Okay, now you're showing me. No, that's correct. That's the correct version. Yeah.
This is the correct version.
Yeah.
You're seeing the whole screen.
We can see the whole screen and one slide only.
Okay. And if I change my slides, is that also
it's
swiftly?
Going ahead. It's proceeding correctly. Yeah.
Okay. Okay.
Excellent.
Thank you. Thank you so much. So good day, everybody. My name is Nema Kahabi, and I'm an MSc student at the University of Cape Town under the Concrete Materials and Structure Integrity Research Unit. My research supervisors are Prof. Hans Boishausen and Prof. Mark Alexander, and I'm here to present my ongoing research work on the effect of partial replacement of natural fine aggregates on concrete durability properties. My presentation outline will include the introduction of my research, part of the background, some of the enhancement techniques that are adapted in the use of recycled fine aggregates, my problem statement, research hypothesis, research objectives and methodology, some of my preliminary results and my discussions, as well as some of my significance and my future work. So starting with my introduction, concrete is mainly made up of water, cement, and about 60 to 80% of fine and coarse aggregates. Now, due to rapid urbanization and advancement in concrete technology, fine aggregates are potentially running out. Now, this challenge is associated with issues such as economic and environmental problems. And most of the times, because when we think about the abundance of sand, we think about the holidays at a wide open beach, but open beach sand isn't ideally the type of sand used for construction, but nonetheless, our lives are built on it. Now, the depletion of nearby deposits of quality fine aggregates forces our industries to haul aggregates from remote areas, which increases the cost and contributes to the overall carbon footprint. Now, as a summary of the quantity used, of the sand quantity used per year, which was conducted by the United Nations Environmental Programme in 2012, it was reported that a production of about 29.6 billion tons of sand was produced in 2012, and that could generally build about 27-meter high and wide wall around the equator, just to summarize that. And for instance, in the Western Cape, most used sand was pit sand from Clipperville and Malmesbury quarries, but however, the overexploitation of the sand has led to environmental degradation and variation in its quality. So this has forced the industry to use different sources of sand, which, for example, crusher sand and dune sand, which are commonly blended together. Now, despite the sources of sand, the use of recycled concrete aggregates as an alternate source of sand has been quite overlooked. Now, to improve the living standard and quality of life without adversely affecting our environment, we need to be aware that both sustainability and development are not mutually exclusive. Now, factually, it is commonly addressed that concrete is by far the most utilized material in the world, second to water, and worldwide statistics from Christian Mayer in 2002 summarized over 10 billion tons of concrete are being produced each year. Now, such volumes require vast amounts of natural resources for aggregates and cement production. Now, although concrete production in general is a friendly environmental material, the production of cement is not. And in addition, it has been estimated that the production of 1 ton of Portland cement causes approximately 1 ton of carbon dioxide into the atmosphere. So the demolition, and disposal of concrete structures and pavements, etc., constitutes another environmental burden, which is the construction debris. And this generally contributes to a larger fraction of our solid waste disposal problem. Now, in concrete, the concrete use in general being at the center stage. Now, hence what was a success story has turned both causer and victim of its own destruction. Now, number of ways that we can adapt in the concrete industry to comply to demands of sustainable development and green environment definitely include things like supplementary cementitious material, the use of supplementary cementitious material, the improved mechanical and durability properties through applications such as admixtures, adequate mixing designs and adequate mix design, and as well as curing, the reuse of water for countries with without abundance of fresh water. And lastly, which is more focused into my presentation today, is the reuse of recycled material. Now, just to show how much of the recycled material is around, statistics by World Bank Group has estimated that waste generation is at 174 million tons just in the sub-Saharan Africa, and this volume is expected to increase to 2.2 billion tons every year by 2025. And building material itself, or construction and demolition waste, accounting to about half of the solid waste generated every year. Now, some of the characteristics of RFA in concrete, which are properties of RFA against natural aggregates themselves individually, and properties of RFA in concrete, include 7 to 9% lower density by Limbachai et al., twice a higher water porosity by Segurko and Still. These are properties of RFA individually, and properties of RFA in concrete include 60 to 80% lower compressive strength as compared to compressive strength for natural aggregates, 4% higher water absorption, and 12% higher 70-day drying shrinkage compared to those with natural aggregates of the same compressive strength. Now, these characteristics has forced the industry to adapt to various enhancement techniques to help adapt to the use of RFA. And these enhancement techniques include mechanical crashing or mechanical processing, which scientifically improves the morphology of the material, pre-carbonation of the material. This helps to densify the material, the microstructure of the material in concrete, and lessen the permeability of aggressive ions. Heat treatment as well is being done in order to remove the adhered paste, which research also showed that it contributes to the inferior properties of the RFA. The use of supplementary cementitious material as well that densifies the microstructure of the concrete and improves overall strength and durability. And lastly, pre-soaking of the RFA in water in order to compensate the extra amount of water needed for both mixing and high water absorption of the RFA due to the adhered mortar. Now, my problem statement says, is more structured on the research on concrete with RFA, in regards to durability properties, that knowledge in general, that bulk of knowledge is very limited, and it's limited in regards to viability and economic techniques that could be adapted for the use of RFA in the industry. It's also limited in concrete penetrability or transport mechanism of concrete with recycled fine aggregates, also reaction of aggressive ions with adhered cement on recycled aggregates through carbonation and chloride ingress process, and as well as strength increase due to their high water absorption through internal curing. Now, my research hypothesis here is that recycled aggregates may improve when we put recycled aggregates in concrete, it may improve durability of concrete due to the following reasons. So the presence of adhered mortar on recycled aggregates may have anhydrated cement in the new I to Z layer, interfacial transmission zone layer, that can cause a secondary reaction. Now, the secondary reaction may contribute to modifying the rate of penetrability and hence an improved threshold level and carbonation font in general. So why do I think my hypothesis would work scientifically? It's because in concrete, without recycled aggregates, the penetrability of aggressive ions in the concrete matrix is through cement paste only. But in concrete with recycled aggregates, it is through the new cement and the anhydrated cement adhered on these particles. So based on this, my main objective is to evaluate durability properties of concrete containing these materials, and my specific objective is to evaluate physical properties of recycled fine aggregates, to identify optimal mix design in terms of replacement level of fine aggregates and assess its influences on both fresh and hardened concrete properties, to determine the influence as well of different replacement levels of recycled fine aggregates on compressive strength and durability of concrete, and as well as to investigate the transport properties, that is permeability, subsivity, conductivity, and diffusion, and overall behavior of concrete made with replacement levels of different replacement levels of recycled fine aggregates. Now, in my research methodology, I conducted tests on physical properties of concrete fresh and strength properties, and concrete durability properties. I did this because it is important to remember that strength does not generally equal durability properties of concrete. And so far, most of my interpretation of the results is a work in progress and is subject to reinterpretation. And due to that methodology, I came up with a mixed design that has 6 mixed designs and 6 mixes, including 2 water binder ratios at 0.45 and 0.6, as well as 3 recycled fine aggregate replacement levels at 0%, 25%, and 50%. And during my mixed design, I would like to show that my coarse aggregates and my water are constant. My cement also was constant with respect to water binder ratio that was adapted, and only fine aggregates portion was varied. And none of the enhancement techniques that I spoke about were also adapted in order to solely investigate the effect of RFA without any variables in it. Now, these are just some of the pictures when I was doing my particle size distribution. And this is a picture of my material retained at the 4.75 millimeter sieve. This is my 2.36 millimeter sieve, also retained at 1.18 millimeter sieve, 0.6 millimeter, 0.3 millimeter, 0.15, and 0.07 millimeter sieve. And as I start speaking about my results and my compressive strength results, I try to put them in 2 different graphs. And this first graph explains that at 0.45 water binder ratio, higher compressive strength values were observed than 0.6 water binder ratio. And this can be concluded due to the denser microstructure in the lower water binder ratio, as well as at both water binder ratios, the highest strength was observed at the 25% replacement mix overall. And at 0.6 water binder ratio, the 25% replacement mix showed the highest strength increase, more than the 0% and the 50%. There's also a gradual increase of strength from the 0% mixes to the 25% mixes. And in addition, at 50% replacement level, early age strength is lower, but quickly increases by 28 days and slightly higher than 0%. Replacement level at 112 days. And these results could be inferred from some of the literature that suggests that since RFA can store more water and this water can be released into the new concrete and over time continue to feed the cement for a longer period of time, which increases strength. And hence it is true that maybe the hydration process progresses with replacement of RFA at 25% due to these results. And part of my analysis also suggests that part of the gradual increase that I get in strength in the lower water binder ratio could be contributed to the adhered cement providing extra calcium silicate hydrate to the matrix, while the higher increase of strength in the higher water binder ratio could be due to the secondary reaction caused by the extra water stored in the material facilitating internal curing. Now, it is also observed that concrete mixes increase gradually in strength than recycled aggregate mixes. And from my second graph here, which puts the increase of strength age-wise at 3, 7, 28, and 112 days, it shows that at 3 days, my highest strength is found at the 25% of RFA for 0.45 water binder ratio. And at 7 days, highest strength is found at 25% replacement level for both water binder ratios. And at 28 days, control mix or the control one or the mix one showed a slight higher strength than the 25% mixes for 0.45 water binder ratio. But at 112, it shows a higher overall strength. And in my carbonation results, so at 28 days, after 28 days exposure of carbon dioxide gas exposure, so 10 millimeter slices were cut, from the sides that allowed carbon dioxide gas through the concrete cubes, and 12 readings were recorded per concrete mix. For the accelerated carbonation test, 2 concrete cubes were used per mixes and 6 readings taken per cube. An average of 2 sides of the carbon dioxide depth on the slides were also measured to get a representative depth as shown above. And this 28 days results also showed that concrete mix had more carbonation than so they showed that the control mix 2, which had the 0.6 water binder ratio, had more carbonation than control mix 1, and this could be generally attributed to the higher porosity and hence a less dense microstructure that allowed penetration of the gas caused by the higher water binder ratio for the control 2, and mixes that had partially replacement of RFA were less carbonated than mixes without RFA. And then in addition, at 0.45 water binder ratio, mixes with RFA showed no amount of measurable carbonation at 28 days, and at 0.6 water binder ratio, mixes with RFA showed a less amount of carbonated depth than the mix without RFA. And most of my error bars just represent an average of 12 readings per concrete mix. And part of my analysis as to why there is a lower amount of measurable carbonation is that in the mixes with RFA, which is subject to my hypothesis, is that more cement in the mix can provide more material for carbon dioxide to react with carbonation front when the carbonation front progresses. And so the formation of more calcium carbonate from the carbonation process as well can be the cause of a dense microstructure and hence blocking more ingress of aggressive ions into the concrete matrix. In my durability index—
1 minute, Nima.
Okay, it's okay, Prof. In my durability index test results, I'm using this guide that was summarized by Prof. Alexander, Dr. McKenke, and Prof. Balim in 1999, that in my oxygen permeability index results, according to the criteria adapted for concrete durability test, the OPIA results, which is calculated as the negative log of Darcy coefficient of permeability, indicate an excellent concrete. Despite having different replacement level values of RFA, all mixes showed excellent results, and the water subtivity results ranged between 7.8 to 9.5, which indicated good quality, not excellent, but good. And the WSI index also represents the rate of capillary suction as well as the water penetrable porosity of concrete. And most of the CCI chloride conductivity index results also indicated or ranged between 0.9 to 1.5, which indicated that the mix were also of good quality, except the 50% replacement of RFA for the 0.6 water binder ratio, which indicated a 1.53 value that showed poor quality. And the CCI values give an indication of good concrete, basically, with a low penetrability influence. Now, at 0.45 water binder ratio, the results indicated a lower CCI for 25% replacement and for 25% replacement compared to the 0% and the highest SCI value for 50% replacement compared to the 0% replacement level as well. Now, these two results remain constant.
Wrap up now.
Okay, Prof. They remain constant for the 0.6 water binder ratio, except for 0% and control mix. And the significance of my research is to enlighten the industry about alternative resource of aggregates and provide a viable practical application for the material. Also contribute knowledge to the importance of using recycled fine aggregates in the on concrete strength and durability development, as well as assisting changing the narrative of concrete waste to a concrete resource. And my future work is going to be on analysis of microscopic investigation, tests for chloride ingress through bulk diffusion, accelerated carbonation tests at 2 more ages. And yeah, thank you.
Sorry. Thank you very much for that, Nima. And sorry that you had to be accelerated at the end. Yeah.
It's okay.
There is a question.
Okay.
Are the particles finer than 75 microns removed from the fine aggregate used in the study? If not, was workability of the concrete with the RCA affected? Did you get that?
Yeah. Yes, absolutely. Okay. So for the first question, the particles were not removed. I just sort of didn't show the picture there because I had so many pictures to show. I included every material all the way to the pan, and that sort of didn't also. I got lower workability, Prof, but my workability was. I could vibrate my material, my mixes, and I could still get like workable concrete, but it was lower. Most of my concrete mixes had a higher workability than the 25 and the 50% replacement level on the 0.45 water binder ratio. But at 0.6, I got like very comparable workability values.
Okay, thank you. This is a question from me. Oh, sorry, there is another question. There seems to be a difference in the influence of the percentage replacement of aggregate at different water binder ratios. Why do you think this is? In other words, the effects of the percentage of replacement seems to be affected also by the water binder ratio. Why should this be?
Well, when we were making the assumption, Prof, on what water binder ratios to use, we tried to use a water binder ratio that would give us a dense microstructure and a water binder ratio that could be used in maybe even non-structure applications. And so we sort of adapted to the 0.45 for higher or a denser microstructure and 0.6 for a lesser, so as we could see how that effect of the adhered cement paste on these aggregates could sort of work in 2 different water binder ratios. And so far
you've become good at ducking. You've ducked the question, but that's fine. Manu's question is actually quite important, and it may need a little bit further investigation. I want to raise a question about the effects on compressive strength.
Okay.
As I understand it, you were replacing dune sand with effectively the dune sands are weathered sands, whereas you're replacing it with concrete, what must have been more large aggregate, crushed rock, virgin rock. And do you think that has had an effect? The fact that you've had a stronger aggregate than say, possibly the dune sand, would that likely explain some of the strength effects that you will see?
Well, I do think so, but just to correct there, it's so that's why I tried to explain that in the Western Cape they use a blend of both dune and crusher sand. So in my replacement, Prof, in the control mixes, I only have 0% for the RFA, and then I have 50% of dune and 50 of crusher. And in my second one, which has the 25% of RFA, also has 25% of crusher sand, but the dune remains constant, 50 for all my mixes. So the dune.
Okay. Then my question is not relevant, but it's still we need to think about it.
Yes,
But okay,
absolutely.
well, yeah, certainly. Let's stop there. We're exactly on time. Thank you very much. First of all, I want to say thank you to both our presenters, to Ram and to Nima, for a very interesting conversation, presentation, and for kicking us off on this workshop to what promises to be a very interesting discussion. It's now my pleasure. I understand that Professor Alexander has, in fact, I did see him linking. There he is, there he is. And I'm going to hand over to Professor Alexander. Mark, thank you very much. Over to you.
Thank you, Professor Ballum, and good morning, everybody. It's very nice to be a part of this workshop, and thanks to all the students who have taken the trouble to set this up. What I consider to be a very exciting occasion already has given us some certainly some food for thought. So we have another session now, and with two sets of presentations, or two presentations. According to my watch, we're just a little short of 11:30 South African time, which means we're just about on time, a little behind, but that's fine. So I think at this stage, then, I'm going to hand over to the next set of presenters. These are two students from the University of the Witwatersrand, final year civil engineering undergraduate students there. So we've got a whole range of students here, all the way from doctoral students through to undergraduate, final year undergraduates. And the students involved here are Lepogo Maleka and Khadimo Lucas Moshla-Tlole. And you can see the title is The Effect of Masonry Rubble as Fine Aggregate on Concrete Compressive Strength and Durability. So I'm giving it over to the two students. I'm not sure who's going to speak first or if you're going to do a duet, but I'll leave it up to you. So please proceed now. Thank you.
Thank you, Prof. Alexandra. I'm just going to try and share my screen, and you'll tell me if you can see it. Is my screen visible, Prof?
Yes, it's there. You just need to go to the full presentation mode. That one. There you go. That's fine. Very good.
Okay, thank you, Prof. Good day, ladies and gentlemen. My name is Lepogo Lucretia Maleka, and I am from the University of the Witwatersrand. And today, along with my colleague, Mr. Khadimo Moshla-Tlole, will be presenting our investigative project on the effect of recycled masonry fine aggregate on concrete durability and concrete compressive strength. The investigative project was conducted under the supervision of Professor Ballum and Ms. Kanji. I'll be taking you through the first half of the presentation, which is the project background and the project scope. Mr. Moshla-Tlole will be taking you through the second presentation, which is on experimental findings, optical macroscopic image assessment, and the conclusions and recommendations. Firstly, looking at the project background. The project came about due to rising concerns of issues on construction waste disposal, environmental impact of aggregate extraction, and the continued demand of aggregate leading to scarcity. By investigating the effect of recycled masonry rubble as fine aggregate on durability and concrete strength, we can determine their applicable use in construction and thus reducing construction waste from demolitions at landfills and disposal sites, and also reducing transportation costs to these sites. Our project scope began with the collection of rubble material. Sorry about that. Rubble material, and the masonry brick was hand collected at a random informal site. As you can see, where I'm pointing with the laser. Some of the bricks collected contain mortar, as well as paint, some of the paint that was left onto the bricks. The investigation contained 3 water to binder ratios of 0.4, 0.5, and 0.6. A referent mix containing 100% of andesite sand, where the water and stone content were kept the same for the andesite concrete as well as the brick concrete. Once the masonry bricks were collected and brought to the laboratory to prepare the bricks as samples for use in concrete, sample preparation began by the discarding of bricks that were contaminated with contaminants that can be seen by the naked eye, such as pieces of metal or wood. After the discarding of the contaminated bricks, we began primary crushing by using a hammer and then secondary crushing by using a crushing machine. The third part of our project scope required determining the grading analysis of the andesite sand. The sieve analysis resulting in the grading presented by the green line as shown on the graph. It's below the upper and slightly below the lower limit, which was found from the literature. Once the sieve analysis was done, the finest modulus FM of the andesite sand was found to be 3.26, which is higher than the upper limit FM of medium fine aggregate, which is 2.90. Sieve analysis of andesite sand resulted in coarse-grained sand. Once the grading analysis was done, the crushed brick was then sieved and reconstituted to match the grading and fineness modulus of the andesite sand. The reconstituted, the crushed brick samples can be seen on the picture on the side, on the right-hand side, with the 4.75 millimeter sieves seen shown, and the 2.36 millimeters and the 1.18 millimeter constitutes of the crushed brick sand. Secondly, we're going to be looking at the project scope, looking at the mixed design. The mixed design was the fourth part of the project scope, and before the mixed design could be done, a pygnometer test was performed to determine the density of the brick and mortar which will be used in the mixed design. The relative density of the brick and mortar combined was 2.67 for the crushed brick, and the which is compared to the density of the andesite sand, which is 2.92. The andesite concrete design was computed first as shown in the table with the, was computed first as shown in the table while containing 100% of the andesite sand. The brick concrete was computed secondly with 100.
We seem to have lost the sound. Are you back?
Can you hear me now, Prof?
Yeah, I can hear you now. Okay, carry on.
Okay. The trial mixes of the brick concrete with 100% replacement of the andesite sand resulted in harsh and unworkable mixes, which led to the decision of replacing only 50% of the andesite sand with the brick sand. A plasticizer was used to improve the workability of the brick concrete mix and to provide a more even distribution of the binder particles throughout the mix. I'll pass on to my colleague, Mr. Mhlatlulo, who will be continuing on the influence of masonry, rubble as fine aggregate on the compressive strength of concrete as well as the durability indexes. Thank you.
Good morning and good afternoon, ladies and gentlemen. As my colleague already mentioned, I will be taking on the presentation from this point onwards. My name is Khadimou Lucas Mhlatlulo. We are both doing final year at Wits University doing civil engineering. I'll be presenting about the influence of masonry rubble as fine aggregate on concrete compressive strength. Once the andesite concrete and the brick concrete mixes were cast and cured, compressive strength tests were conducted at 3, 7, and 28 days of curing. The results showed that it is possible to achieve a high strength concrete using recycled brick at all 3 ages of testing. The data showed a recorded strength gain of brick concrete relative to the andesite concrete ranges from 5% to 20%, with the brick concrete being stronger than the andesite concrete. The significant strength gain of the brick concrete can be attributed to the use of superplasticizer, which causes a better dispersion of cement as well as better hydration. The high strength gain may also be due to the significant sand content in the 0.5 and 0.6 mixes as shown on the graph. The compressive strength test results also show a correlation between the water to binder ratio and the compressive strength of both the andesite and the brick concrete. At 28 days of testing, the compressive strength of the brick concrete lies between 43 and 76 megapascal, while the strength for the andesite concrete lies between 37 and 71 megapascal, with the water to binder ratio being the main influence of strength as shown on the graph. Now, from this point onwards, we will be looking at the influence of masonry rubble as fine aggregate on concrete durability. We will first start by looking at the result of the oxygen permeability index test. The results show that the correlation between water to binder ratio and the OPI of the concrete is only seen on the andesite concrete for 1 day curing. But the same cannot be said for the brick concrete. The OPI of andesite concrete decreases with the increased water to binder ratio, meaning the andesite concrete has a high permeability. Looking at the graph, it can be seen that the 0.4 mix ratio is an anomaly that disrupts the correlation between the water to binder ratio and the permeability of the brick concrete, leading to the result being inclusive. If we discard the 0.4 mix ratio for the brick concrete, it can be seen that the OPI values of the brick concrete are higher than that of the andesite concrete, meaning the brick concrete is less permeable than the andesite concrete. This is expected to be as masonry brick is more porous than the andesite stone. And the OPI values of both the andesite brick and the concrete, the andesite concrete and the brick concrete remain within the range of South African concretes of between 8.1 and 10.5. Furthermore, as we look at the OPI result after 28 days of curing, no correlation is shown between the water to binder ratio and the OPI of both andesite and the brick concrete. This is due to a 0.4 mixed ratio, again being the anomaly that disrupts the correlation between water to binder ratio and the permeability of both andesite and the brick concrete. Generally, the longer the cure, the higher the OPI, resulting in the concrete being less permeable, which is the case for both the brick and the andesite concrete when we discard the 0.4 mix ratio. Reference to the previous slides, the andesite concrete shows a high increase in the OPI values compared to that of brick concrete, as the concrete is cured for a longer period. A further showing the andesite concrete is less permeable than the brick concrete. When looking at concrete durability in terms of water sorptivity index, according to the literature, when the water to binder ratio increases, the water sorptivity index increases, which results in the high water absorption, meaning less resistance to moisture ingress. On these results, there is a correlation between water sorptivity index and the increase in water to binder ratio for the andesite concrete. But the brick concrete, there is no clear correlation, and the brick concrete results depict a constant water sorptivity index regardless of the change in the water to binder ratio. This is for 1 day curing. At 28 days of curing, the data suggests a more constant sorptivity in the brick concrete with water to binder ratio, but with higher water sorptivity index compared to the 1 day curing. whereas andesite concrete show a difference sorptivity that fails to correlate with the water to binder ratio. The 0.4 water to binder ratio again comes across as the anomaly in the results displayed. This creates inconsistencies in the results which limit us from determining the durability indices and thus prevents us from comparing the quality of the andesite concrete with that of the brick concrete. After looking at the durability index results, we moved on to the optical microscopic image assessment of the brick concrete. This dark brown color here on the first image is the sand particle embedded in concrete during the casting, and the whitish color here circled in blue is the sand particle inside the brick particle that was included during the manufacturing of the clay brick. And this part circled in yellow, this is the andesite particle. Coming to the right-hand side image, this part here circled in red. This is the line between the brick and the cement paste. It's the interface that shows a perfect bond between the brick particle and the cement paste, which also shows...
Adimo, you have only about 1 or 2 minutes left, so can you move to the conclusions as soon as possible, please? Thank you.
Okay. Based on our experimental results and analysis, we can conclude that concrete made from replacing 50% of andesite sand with crushed recycled masonry exhibit a high compressive strength behavior at all stages of curing when plasticizer is added to the concrete mix. The effect of crushed recycled masonry on durability is inconclusive due to lack of correlation between the OPI and water to binder ratio. And water to WSI and water to binder ratio results at different curing days. OPI and WSI results suggest andesite cubes to be more permeable and less resistant to moisture ingress compared to cubes made from crushed recycled masonry. Recommendations is additional research should be done to compare the compressive strength and the tensile strength of the concrete made with recycled masonry. More research should be done on the effect of masonry rubble as fine aggregate on concrete durability. This brings us to the end of this presentation. We thank you, Ralevo.
Thank you very much. Now I have a real problem here because I have some genuine demolition going on underneath me in this apartment where I am. So sometimes I can't hear anything. So I'm in the midst of a real demolition problem. I'm not sure if we'll be able to use what they're taking out. Anyway, I'll do my best to pose the question and we'll just see how we go. The first question is the following. Does the use of crushed brick as sand, could it have any potential for creating alkali silica reaction problems? I don't know who would like to handle that question, but I'll leave it up to the two students as to whether they can respond to that problem. Would crushed brick give potential ASR problems?
We haven't thought about that one as we only focused on the water sorptivity index and the OPI in terms of durability. So we can't really answer that one.
Okay, that's fine. It wasn't within the scope of your research, so it could be something that would need to be looked in another investigation. There is another question that has also come through here, and that is it possible that the fine brick particles could act as a form of, I think this is meant to be calcined clay, and could this be the reason for the positive strength results rather than just the use of a superplasticizer? Is that question clear, or shall I rephrase it? These brick particles, could they act as a kind of almost like a pozzolanic material in the form of a clay?
Is it possible to repeat the question again?
Yes. Could these crushed brick particles act as a calcined clay, which means could they be partially pozzolanic? And could that be a reason for the positive strength results rather than just the use of the superplasticizer?
Yes, that is possible to have the fine particles of the clay act as a positive effect in the strength of the concrete. This has been shown in the literature, but we haven't actually considered it. We're only looking at the effect that is caused by the plasticizer as well as the influence of the amount of sand we had into the mix.
Sorry, as I say, I'm juggling things here. That could be further looked at. I also had some questions about the calcine, about the superplasticizer as well, but it's another thing that could be looked at. Here is another question. The OPI results seem to indicate better behavior with the brick-based concrete. What was the standard deviation on the results? Do you have any idea of what your variability of your results was?
Pardon, may you please repeat the question again?
Yes, I'll try again. The OPI results seem to indicate, let me just go back to the chat, that seem to indicate better behavior with a brick-based concrete. What was the standard deviation of your results? In other words, how much variability did you get in individual OPI readings, results?
The variations that we got in the different results for the OPI ranged between 0.08 and 0.53, looking at the brick as well as the underside.
Okay.
So it was a minor variation in the OPI results.
Okay. I mean, the results were, in general, they weren't very different. In fact, what surprised me was generally rather low OPI results for your concretes, particularly the andesite concrete, but that could also be due to some other factor. And then I have a last question here, and that is, has the masonry been tested for any other properties? Did you test, for example, porosity, absorption, so on and so forth? Did you test any other properties of the masonry?
No, we did not do this, Prof, because we had quite a limitation in terms of the time.
Yeah.
So we could not do any of those tests.
I think if I could set the, I'm sure that our listeners will understand this, but a final year undergraduate project is a very limited one in scope. And so I think that what these two students have managed to achieve in their undergraduate project is really quite remarkable. And I think they should be very much congratulated on the work they have done. That more or less brings us to the end of your session. So thank you very much, Lepocho and Khadimo, and good luck with the rest of your undergraduate career. If you could take your screen, your results off the screen here now, and so we can go back to the other one. Here we have the next one. So our next speaker is Rohit Prajapati. Hi, Rohit. Nice to see you again.
Hello, sir.
Rohit is a PhD scholar at IIT so he's working in the general area of recycled aggregates, recycled fine aggregates as well. And his topic for the second presentation of the session is thermomechanical treatment for the extraction of aggregates from demolished concrete. Rohit, it's over to you. Thank you.
Yeah, thank you, Professor Mark. Can you see my screen? My presentation is visible?
Yes, it's visible.
Yeah, okay. Thank you, Raj. So I'm going to talk about thermomechanical treatment for recycling of waste concrete. So Ram has already set the background, but just to start, the there is a problem of disposal of C&D waste, and it's being illegally dumped, and sometimes we are landfilling it, so we are not properly utilizing the resources. And there is another part where the construction, there is a boom in the construction, and the aggregate demand is going high. So in India this year, the aggregate demand was around 5.5 billion tons, and the waste, that the C&D waste that is generated is around, as Ram also pointed out, is around 700 million tons per year. And to again say that the recycling capacity of currently installed capacity is only 1.2 million tons, which is very less. So like we can channelize this waste and use it as a resource, and we can fulfill the demand of aggregates as well. So again, we all know that the C&D waste is the waste materials that are produced in the process of construction, remodeling and repair of old structure, and also demolition of existing structures. So in India, around 1/4 part of the total C&D waste is concrete. So in my presentation, I'll be talking mainly on this concrete part. So there is a limitation. If you see all these international codes, only the 100% replacement of aggregates to the natural aggregate is 100% only in low grade concrete or non-structural grade concrete, and other replacement percentage are only a limit to around 20 to 25%. So there's a limited applications of recycled aggregate in structural concrete. So what are the reasons? So now if you look at natural aggregate and recycled concrete aggregate, there is this attached mortar adhered to the surface of the stones. So this is responsible for very high water absorption, could be high like 4 to 5 times. And of course, it also reduces and lower down the mechanical strength. And if you completely replace this recycled aggregate with natural aggregate, the compressive strength could reduce up to 30%. So what is the difference in normal concrete and the concrete where we have replaced or used recycled concrete aggregates? So if you see in normal concrete, there is one type of interfacial transition zone, which is between the aggregate and the mortar. But if you look at the system of recycled aggregate concrete, you have multiple ITZs. You could have ITZs between many ITZs between new cement paste mortar or the old adhered mortar and the stone. So there could be multiple ITZs, and we know that ITZs are the weakest zone in the concrete. So this influence is magnified in recycled aggregate concrete, though we have a presence of multiple ITZs. So if you look at the failure modes, so there could be 5 failure modes in recycled concrete aggregate concrete. First is the crack could initiate through the new mortar, and it could be at the interface of the new mortar and the old mortar, and it could also be through the old other mortar, and again it could be through the ITZ, which is between old mortar and the aggregate itself. And lastly, it could also go through, or it could pass through the original aggregate. But out of these 5, these 2, mode 3 and 4, which is through which is related to the old adhered mortar, is found more common. So what are the treatments to overcome this problem? So you could have like 2 types of treatment. One is you remove this mortar, or there could be surface modifications using some pozzolanic materials, or you try to modify the surface or densify it. But there could be a problem because you may not be able to strengthen the old adhered mortar and the ITZ between the old adhered mortar and the stone. And so there are other techniques Nima also pointed out. There could be, we could use mechanical treatment to scrub the old adhered mortar, and you could dissolve this old adhered mortar using chemical treatment. There are other methods, microwave heating, ultrasonic cleaning. But this thermal treatment, so thermal treatment has the highest efficiency in the removal of adhered mortar. So first we dehydrate or weaken this red mortar, and with a little effort of mechanical scrubbing or rubbing, we can remove it. So my next slide will be on the thermomechanical treatment we have done. So we have brought the concrete from this demolition site nearby our campus in Chennai, and then we have reduced the size to 50 mm. That was also based on a study where we have looked at different sizes, and we homogenized it to make a homogenized feed because the concrete could be of different strength in a structure. It could be from column, beam, or other parts. So it's important to homogenize it. And then the feed was fed to electric furnace and heated and cooled down. And after that, it was put in the milling machine to remove this this weakened red mortar. So after this, you get these three products, which is coarse aggregate, fine aggregate, and the concrete fines. So so to optimize this process, we have come up with an acceptance criteria. So there is criteria for process and there is criteria for products. So first we look at we have looked at this stringent international standards and recommendations for the aggregate for the parameter as a product of the parameters for aggregate quality. So basically we have picked up two key properties, which is dry density and water absorption. And so we have framed this recommended acceptance criteria, where you have these two parameters for assessing the efficiency of the process. And again, these two properties were taken from this table first. And so this is the criteria for quality, the parameters for quality of recycled product, which are the coarse and fine recycled aggregates. So let's understand. So this figure has like our study has four variables in the blue box. So one is the heating time. So we have two phases. In one phase we have varied the heating time, and then we have the milling process. There are two types of milling were tried. One is using steel ball as a charges, and other one itself by without any charges. And you have this weight fraction here, and the temperature is varied again. So to understand how the total yield of recycled product was calculated. So if you see this first box here, it is of concrete. It is for concrete fines, which is less than 300 microns. Then comes up next is the recycled fine aggregate, and you have coarse aggregate. And at the bottom, this part is the broken concrete, which was not processed, or it was more than 20 mm size. So we say this is an unprocessed material. So if you want to calculate the total yield of recycled product, you have to get the sum of these three: the concrete fines, fine aggregate, coarse aggregate. And another parameter for assessing the efficiency of the process is the amount of concrete fines. If you are able to generate more and more concrete fines, that means you are cleaning both fine and coarse aggregate. So let us look at the first part where we have tried to look at the heating temperature and the charge. So you can see that as we as the temperature was raised, say, so the total yield of product was increased. So you can see that unprocessed material is going down here. And between the two cases where A is for without charge and B is for with charge, where we have put steel balls along with the concrete feed during the milling process, you can see in the milling with charge, we generate more fines because we are cleaning more and more aggregate. So with this, we conclude that treatment at 500° C yields acceptable materials, and milling with charge, of course, it increases the efficiency and generate more fines. With this, we are simultaneously, after each trial, we are also monitoring the product quality, which is the coarse and fine aggregate quality, in terms of dry density and water absorption. So just to give you an example, here I have put, this is for dry density for coarse aggregate. So we have set this acceptance criteria from taken from international standards and recommendations. And then we also have tried to compare it with the natural material, which is in this case is granite aggregate. So there also we see that as we increase the temperature, the dry density improves because we are removing more and more dead mortar. And same goes with the water absorption. The water absorption decreases and it's coming closer to 1%. So increase in temperature also improve the dye density and absorption characteristics, and the material obtained at 500 degrees C complies the criteria. But in some cases, it could comply the product quality, but it may not qualify the process efficiency criteria. So we have to look at both things. And for the second phase, we have kept the heating temperature at 500 degrees C constant, and then we have tried to vary the heating time. So we have from 120 minutes to 30 minutes. So we observed that both cases where the heating was done for 60 minutes or 120 minutes yields the material that satisfy our acceptance criteria. So this heating for 1 hour was taken so that we'll save some energy in the heating part. So after this two process, this was our optimized methodology where we reduced the size to 50 mm, and then heating was done at 500 degrees C for 1 hour. And after ambient cooling, we are milling this concrete feed with the steel balls with charge. And then after sieving, you get all these three products. So after this, you get this clean aggregates. So we can see that that is very, very less. We are able to remove 96% of this attached mortar on the coarse aggregate part. So just to compare all these aggregates, so we have here natural aggregates. For fine aggregate is river sand, and then you have granite aggregates for coarse aggregate. So we have tried to compare the properties of this treated material with the standard material and other materials, such as the alternative for fine aggregate is the crushed sand and laboratory crushed and industrially produced recycled fine aggregates. We have seen that the properties have improved when compared to the conventionally produced recycled aggregate. Same goes with the coarse aggregate, and we were able to bring up the dry density and the water absorption. We were able to bring down to close to 1%, and the mechanical properties as well was increased. So these treated aggregates have better quality than the conventional recycled aggregate, where just the crushing is involved. And so again, to look at this failure modes. So we have removed this old other mortar. So we have eliminated these two possibilities where the failure could go through old other mortar, or it could go through the ITs between the aggregate and the old mortar. So this also could be seen in the next test, where we have tried to replace this coarse aggregate with natural granite aggregate at the replacement level of 20, 60, and 100. So we could observe that even if we replace this with 100% this granite aggregates with the treated recycled aggregate to the 100%, the compressive strength was not compromised even at full replacement. And so finally, I would like to acknowledge the funding from UKRI and DST, Government of India, and the UK scene for financial support. Thank you.
Thank you very much, Rohit. Excellent presentation, and thank you for sticking to your time so well. A number of questions have come up. So I'm going to start with the first one. And this one is, as would be expected, on the question of the energy aspect of these recycled aggregates. With such a high energy dependent method, these temperatures up to 500 degrees, will recycled aggregate still provide a sustainable solution? In other words, have you looked at the energy metrics overall?
Yeah, so we have been monitoring the energy, but there is another part of this research which I have not shown here, where we have tried to address this high energy demand by replacing the mode of heating from electric furnace to solar heating. So that could bring down the energy cost and the footprint as well. So that's the other part I have not included here. I hope maybe in the next workshop and sometime I can present that part.
Okay, but can you give us some idea? Is this heading in the right direction or not?
So what we have seen is like for 10 kgs of concrete feed, we need 2.5 kilowatts of electrical energy. But still, we have not worked out the full picture. So I cannot answer all the questions. But I think there are some methods of solar heating where we can directly heat this mass, and we will be able to do the same process with that.
Thank you. And then the next question, Rohit, is, well, the first question is the same as the one you just answered, but is there a standard procedure to calculate the quantity of adhered mortar in recycled concrete aggregates?
So there is one method suggested by ASTM, and there are some methods where this same heating and mechanical rubbing is done, and then there is also another method which use chemicals such as sulfuric acid and HCl. So we try to dissolve this attached mortar, and then you take the weight after dissolving it, and that's how we done. But as I remember, I think there is only one ASTM standard or as a paper on that.
Okay. I think we'll hear a little bit more about acid treatment later on in the afternoon session, at least the South African afternoon session. You're already in your afternoon. The next question is very similar to the previous ones, and that is around cost effectiveness. So we've got to consider energy demand and also the cost.
Right.
Have you got a sense of cost effectiveness of this approach?
Not yet.
Okay, then I have another question, and that is, in your process, you break down the aggregate into 4 fractions, the sort of the larger fraction that maybe you can still do something with. Then you have this, your sort of recycle, the coarse aggregate, the fines down to 300 micron, and then the lower, less than 300 micron. Why do you differentiate between the 2 sets of fines there, the down to 300 and then less than 300? What is the reason for differentiating, and why did you choose 300 micron as a differentiator?
Yeah. So what we think is in these kind of treatments where, especially with this thermomechanical treatment where you have this milling involved, there is a high amount of fine material is produced. And we think that this material can be, we could have more environmental benefits if we use it somewhere else. That like there are some studies which says that it could be used potentially as raw meal for clinker production, and it could also work as pozzolana or something like that. And so why 300 is when you use more and more fine sieve, it's very difficult to sieve at such a large scale. And also it also improves the water absorption of the fine aggregate part. So we thought that if we separate and use it somewhere else, we can get more environmental benefits, and the other side also the water absorption of the fine aggregate also improves.
Okay. Thank you. That's an interesting answer. Were you able to characterize those 2 fractions? Did the less than 300 microns have a significantly higher sort of cementitious content?
Yeah. So we have done acid dissolution test, and we see that 50% part is quartz, and other are calcium bearing phases. But we have just done the characterization, but we have not done any reactivity test or like that.
Okay. Thank you, Rohit. There are no more questions that have popped up on my screen here. So I imagine that that is the end of those questions. And let me thank you, Rohit, again for your presentation. We're just about exactly on time. And so my job is to thank the two sets of speakers, the 2 students from WITS, the final year students, and then the student from IITM, for giving us a very interesting and entertaining session with lots, I suspect, more questions than answers at this stage. But I think that's what research should do. It should always throw up more questions than it answers. So congratulations to these students, and thank you for your effort in putting together your presentations.
So to chair this session, now I invite Professor Gettu, Institute Chair Professor, who will now moderate the sessions and take it forward. Professor Gettu, over to you.
Hello everyone, I am Ravindra Gettu from IIT Madras. So it's a pleasure to be with all of you, and I see that the sessions are very well attended, and the participants are doing a great job, both in the presentations as well as in the question answer sessions. So we'll start right away with the next talk. It's on the enhancing the performance of fine recycled aggregate concrete by Ichebadu Amadi from the University of Cape Town. So Ichebadu, you can turn on your video, please, and you can start presenting. So you have 15 minutes.
Hello, everyone. Can I please share my screen, please?
You should be able to. Rohit, can you make Ichebadu a co-host?
Yes, sir. He is already a co-host.
It's not showing like that.
Okay. Now, can you try, please?
Yes, please.
Now you should be able to. You could also turn on your video.
Okay, I will after the presentation.
Great. Yeah, we can see it. Please go to presentation mode.
Okay, can you see it now?
Yes, we can. Please start.
Okay. Hello, everybody. My name is Ichebadu Amadi. I'm a PhD candidate in the University of Cape Town. My supervisor is Professor Hans Boshausen. My co-supervisor is Professor Mark Alexander. Today, I will be discussing about enhancing the performance of fine recycled aggregate concrete. Here is an outline of my presentation. I'll begin with the background and the motivation behind my studies. There is a global shortage of natural aggregate, especially sand. Presently, sand is extracted at a rate that is more than the rate of natural production. This has led to environmental issues such as coastal erosion and the loss of biodiversity at sand mining sites. Also, socioeconomic issues have also been observed, such as illegal sand mining and sand wars across the globe. One way of sustainably addressing these issues is the use of recycled sand from recycled concrete, from the concrete components of construction and demolition waste. Generally, recycled aggregate is characterized by a weak and porous adhered cement paste, which originates from the old concrete. Also, recycled aggregate has irregular shape. Usually, the shape is elongated, it is very angular, and it also has a rough texture, which is a consequence of the production process, basically the crushing process. Now, all of these, now when you compare these, the properties of recycled aggregate to natural aggregate, you realize that recycled aggregate is generally more porous, it has a high water absorption, it has low density, and it has a low abrasion resistance. Consequently, this has impacted on the workability properties, the mechanical properties, and the durability of the concrete produced from recycled aggregates. Now, my problem statement. The use of fine recycled aggregate for structural application is restricted. This is because it does not meet the strict requirements for structural concrete. Now, the presence of attached cement paste, especially in the finer fractions of fine recycled aggregate, is largely responsible for the poor quality of fine recycled aggregate concrete. Now, usually, the amount of attached cement paste, that is the ACP, increases as aggregate sizes reduces. Therefore, there is more ACP in the finer fractions of fine recycled aggregates. Presently, there is a lack of understanding on how to improve the properties of fine recycled aggregates and fine recycled aggregate concrete. This is because previous studies have focused on the coarse recycled aggregates because it has less adhered mortar. The challenge, therefore, is how to effectively reduce the overall ACP content and the porosity of fine recycled aggregate so as to make better concrete. The aim of this research is to develop procedures on how to enhance the properties of fine recycled aggregate for structural application in concrete production as a large-scale replacement for natural sand resources. To achieve the research aim, this study will basically focus on the following objectives. One, to reduce porosity and strengthen fine recycled aggregate concrete using supplementary cementitious materials as pozzolanic slurry. We'll discuss this much later. Secondly, we would like to reduce the overall ACP content of fine recycled aggregate by systematic substitution of the finer FRA particle sizes with natural sand. We also hope to optimize fine recycled aggregate and fine recycled aggregate concrete performance through processing, mix design procedures, and curing. For now, this research is still at the early stage. We are yet to obtain lab results. Therefore, I will give a brief overview of the different enhancement techniques and then focus on the use of pozzolanic slurries, which is being adopted by these studies. Typically, enhancement techniques involve the following procedures: the removing of attached cement paste, the improving of the recycled aggregate shape, that is general morphology, reducing elongation, reducing angularity, and all of that, and also improving on the rough texture. Then it's also basically will involve reducing the porosity and strengthening the bond in the recycled aggregate concrete. A few of these enhancement procedures will be discussed here. The first is mechanical processing. Mechanical processing involves crushing, ball milling, abrasion, and other mechanical processes. Here, recycled aggregate shape is generally improved, and of course, the rough texture is also improved. The consequence is that there is a reduction in the overall amount of attached cement paste, and consequently, the properties of the recycled aggregate concrete is improved. Usually, the mechanical properties and the durability properties will be improved. However, it comes with some disadvantages. First, there's the development of micro cracks due to the attrition process of the mechanical crushing. And these micro cracks, as we know, can induce durability issues from the concrete produced. Secondly, the quantity of the recycled aggregate processed is reduced. This is because weak aggregates are broken down to fines, which is usually discarded. And in my case, this process is not suitable for fine recycled aggregates because the ACP and of course the weak aggregates are broken down into fine fractions, which may be a problem. A second enhancement technique is the use of pre-soaking in acid. Now, pre-soaking in acid basically involves immersing recycled aggregate in an acid medium to dissolve the attached cement paste. Afterwards, the recycled aggregate is washed to remove the acid. Now, this process reduces the ACP, and subsequently the concrete properties are improved. But then there are also disadvantages. The first is that the improvements from literature has not been very significant, just minor improvements in the mechanical and durability properties. Then the second issue is that this process may not be economical and cannot be practical considering industrial application. And also depending on the acid concentration, the recycled aggregates can be damaged, there can be degradation, and this will, of course, impact on the concrete properties. And as we very know, this process may also be a source of hazard. Another enhancement technique will be the use of heat treatment. Rohit has basically elaborated on this. Now, this process basically entails the use of high temperature to dehydrate, to embrittle, and remove the attached cement paste. Here, the ACP content of RA is reduced. This is, and this, of course, largely depends on the heating temperature. We saw from Rohit's presentation that temperatures had to go as much as 500 degrees Celsius to get very good results. And subsequently, the properties of the concrete is also improved, as we have seen. Now, but then there are also disadvantages. There is the development of, due to the high temperatures, there can be thermal stresses which can build up, and this can cause the recycled aggregate to degrade. And of course, these thermal stresses can also induce micro cracks, which may also raise durability concerns for the concrete produced. As you can imagine too, this process involves a lot of high energy demand and with an associated high cost. This, of course, raises concerns about the industry practicality of this approach. In my case, for fine recycled aggregates, we expect Rohit to tell us if this can be used to enhance my material. I move on to another enhancement procedure, the use of carbonation. Yeah, carbonation can be used to enhance the properties of recycled aggregate. Recycled aggregate is treated with CO2, usually in a carbonation chamber. The above reactions occur. Calcium hydroxide and calcium silicate hydrate from the hydrated cement paste of recycled aggregate, of course from the attached mortar, react simultaneously with carbon dioxide to produce calcium carbonate, as you can see from the reactions here. The calcium carbonate produced fill the pores and densify recycled aggregate. Subsequently, recycled aggregate water absorption is reduced. The mechanical and durability properties of the concrete produced is improved. This method is suitable for fine recycled aggregates because of the extra calcium hydroxide reserve due to the high ACP. And also the high specific surface area of fine recycled aggregates can increase carbonation rate and therefore produce more calcium carbonate, which will further densify the recycled aggregate. But on the downside, this process may not be economical considering industrial application. This is because the use of carbonation, because the use of carbonation chamber to induce carbon dioxide. Otherwise, if we depend on atmospheric CO2, the process may actually take a long time, which may not be in our best interest. Another procedure to improve recycled aggregate and recycled aggregate concrete will be the use of polymer impregnation. Now, common polymers used here include polyvinyl alcohol, otherwise known as PVA, siloxanes, and desilanes. In this process, recycled aggregate is soaked in a solution containing the polymer and the water. The polymer solution penetrates RA pores and forms a thin film around it. The hydrophobic effect of the polymer reduces recycled aggregate water absorption. Consequently, the properties of recycled aggregate concrete is improved. We can see that from this picture here, that there's hydrophobic action, which obviously reduces water absorption. Yeah, on the downside, for this process, very few literature exists for fine recycled aggregate concrete application, so it will be interesting to see what happens. Considering economy and the industrial application, there may be a challenge in this process. And here we go. One of the very major methods of improving this material would be the use of pozzolanic slurry. Here, supplementary cementitious materials, SCM, can be used to enhance the properties of recycled concrete. In this process, the recycled aggregate is premixed in a slurry which contains SCM, cement, and water. The purpose of premixing is to provide more interaction between the silica present in SCM and the calcium hydroxide reserve of recycled aggregate, thereby enhancing pozzolanic reaction, and formation of more CSH products, which will modify concrete microstructure and, of course, improve concrete strength. The reaction is shown here. As you can see, calcium hydroxide plus silica will give us CSH. Also, in this process, we expect that the micro cracks, which usually is a consequence of the crushing process of this aggregate, will be filled by the pozzolanic slurry and, of course, the products of hydration. Studies have shown that this process can substantially improve the mechanical and the durability properties of concrete. This method also is suitable for my material, fine recycled aggregate concrete, fine recycled aggregate, because of the extra calcium hydroxide reserve, which will translate to more pozzolanic reaction. Therefore, based on economy, based on performance, based on sustainability and industrial practicality, we have decided to adopt this process for this research. On the downside, depending on how you look at it, there is a scarcity of literature on the application of this technique for fine recycled aggregate concrete. This is because most literature has focused on coarse recycled aggregate concrete. Now, to carry out this research, here are some experimental variables and parameters which has been proposed. We're looking at using different SCMs, 3 in number, and we're looking at using different replacement levels for fine recycled aggregates. Then we hope to play around with different particle sizes so as to optimize material properties and, of course, look at the influence of ACP and how ACP reduces across the size spectrum.
Ichebadu, you will have to do your conclusions because you're almost out of time.
Okay, I'm almost there. Here are the tests we'll be carrying out, and we'll look at the aggregate properties, characterize them, measure fresh concrete properties, and then focus more on the hardened properties, specifically durability. On a closing note, it is expected that the use of pozzolanic slurry will improve the mechanical and durability performance of fine recycled aggregate concrete. Also, the systematic substitution of the final FRA fractions will reduce the overall ACP content and, of course, the porosity of fine recycled aggregate. Consequently, we expect this to substantially enhance the concrete properties. Now, these studies will also provide insight on how to optimize the performance of SCMs for recycled concrete application. And on this note, I want to say thank you.
Thank you very much for a very clear presentation. We have several questions. One is about the nature of the recycled aggregates. We know that there would be a mix in terms of the concrete grade because your recycled aggregates will come from different demolition sites. So how can you handle that?
For now, we expect to use laboratory crushed concrete, and we'll also be playing around with concrete from a precast construction yard. The whole idea is that we want to be able to offer, we want to have a concrete of known composition so that we can be able to interpret results adequately. Then moving forward in the future, we can play around with typical CDW waste.
Sure. But when you have to scale up and when the industry will use your results, you could expect that there would be a mix of concretes of different ages and strengths. Have you any thoughts on how that could be handled?
Yes. I mean, this, as you very well know, there's very little literature in the area of fine recycled aggregate concrete. So we want to start from knowns and work towards unknowns. So want to play with concrete of known composition, and hopefully moving forward, we will try our hands on typical waste concrete, and in that case, which will definitely benefit the industry.
Very good. You indicated that the coatings with slurries having mineral admixtures or SCMs were, according to you, the most promising.
Yes.
Yes. Now, do you think that the bond will also be affected? Will it improve or will it worsen when you have this coating of slurry?
The bond is expected to improve. And from literature we have seen on coarse recycled aggregate concrete, the bond definitely improved. The reason is that this interaction using pozzolanic slurry is basically to optimize the performance of these supplementary cementitious materials. We want these supplementary cementitious materials to, interact fully with the calcium hydroxide reserve present in the final aggregates to start the pozzolanic reactions on time. We don't want a case where we have to wait for calcium hydroxide from cement hydration products before we can start generating strength from the SEMs. So we expect the strength, the bond to improve.
What could be the disadvantages of the polymer coating?
The polymer coating, though not within the scope of this work, but some of these materials, obviously, we have to look at the production cycle, we have to look at the cost. Some of these materials are quite expensive. Then you want to consider how can you control these processes, because you expect that these polymers will definitely wrap themselves around the recycled aggregate and form a thin coating around it. So I don't know, those are some processes you may not be able to control entirely, unlike the polymer slurries, where there's a greater measure of control for us.
One last question. Do you have any information on the fire resisting capacity of concrete made with recycled aggregates?
That may not be part of the scope of my work, but typically it shouldn't be much different from normal concrete, conventional concrete.
Okay, so you would expect the same behavior in general?
Yes, please.
Okay, so thank you very much. I think it was a very good, informative talk. All the best in your work.
Thank you very much.
Thank you. You can stop sharing now.
Okay, please.
We will go to the next talk on durability and deformation properties of ASR rubble concrete by Dikeledi Maboa from WITS. Dikeledi, are you ready to share?
I'm trying to share. This will stop other screen.
Okay.
Yes, I'm ready to share. Hi, everybody.
Please do so. Hi. Yeah, we can see your screen. You can go to presentation mode and start.
Sure. Like I said, my name is Dikeledi Maboya, and this is a potential PhD topic that I might be doing. And it's on durability and deformation properties of alkali silica reaction rubble concrete. Right, so change slide. So as I said, at this stage, my PhD is still in the concept stage. There are far more questions than there are answers. And I'll be presenting on my current understanding of ASR and also kind of take you through what the idea is for my PhD. Next slide. Okay. So currently I understand that alkali silica reaction is a chemical reaction that occurs in concrete, and it's between a silica-rich aggregate and an alkaline cement with the presence of water. This chemical reaction forms a gel that expands, causing microcracks. The microcracks make the structure more vulnerable to other chemical attacks, weakening it even more. So with time, you would also see that the SAR, as you can see in the diagram, after the attack, there's gel that forms around the aggregate, and at times it would ooze out into the, to be easily seen by other people as they pass by. Next thing. Oh, this is the wrong slide. Okay, so I just pressed the wrong slide. So there's a network of a network of cracks. So this is one of the ways that you can pick up ASR. You can see a mapping or a network of slides of cracks. So the next slide would be that you've got closed or spoiled joints. Then the next slide is if you have relative displacement, where because of the gel, some parts of some concrete will displace some of the other material, so causing differences in displacement. Next slide. So the ASR problem has been around for a long time. It was first recognized in the USA in 1938. In South Africa, the problem was first identified in structures in the Cape Peninsula, and in the 1970s, it was extensively investigated. So because of this, there has been some method in order to either control or prevent ASR. And as listed, you can see there, they would be used non-reactive aggregate, so aggregates that don't have silica. Then we could use supplementary cementitious material. You can also limit alkali loading. You can use lithium-based admixtures, or you can do limestone sweetening, which is you replace a percentage of the reactive aggregate. Next slide. So in South Africa, we have a number of structures that have been demolished to be reconstructed or replaced because of ASR. So for my PhD, the thinking is that we recover the rubble demolished from the ASR affected structures and use them as either coarse or fine aggregate in new concrete. Next slide. So we are currently looking for the ASR rubble concrete from the Johannesburg M2 East ramp. So once we find it, we will then crush it into either coarse or fine aggregate, then mix it or manipulate it for the investigation. Next slide. So the focus really is on durability and long-term elastic deformation. And so for durability, we're considering looking at the permeability, the corrosion, the freeze thaw. And for the long term, we're considering looking at creep and shrinkage. Next slide. So at a basic level, concrete is considered to consist of 3 phases. So it's a cement paste, aggregate, and interfacial transition zone that you find between the aggregate and the cement paste. So the 3 phases have different elastic moduli that demonstrate the ability of concrete to withstand deformation due to applied stress. So the aggregate and hardened cement paste have a higher ability to deflect elastically than the interfacial zone. And so the aggregates and the mixture proportions affect the elastic modulus of concrete. Next slide. For my PhD, the idea is to introduce multiple phases to concrete. So the phases will be what is listed there in the table. So because we would have found our rubble concrete, we would then crush it, like I said, either into coarse or fine material. Then we would mix that old aggregate with new material. So we would have a phase of aggregate with gel-filled cracks. We would then have an ASR gel on aggregate surface. We'd have the old interface. Then you'd have the paste adhering to the old interface. Then we'd have a new interface. Then you'd have a new hardened cement paste. So we're interested in knowing how then this will behave through durability and also long-term deformation. Next slide. So at the moment, the variables have not been decided on, but these are some of the considered variables. So we're looking at the types of aggregates. Should we just keep the rubble concrete as the aggregate or mix it with something else? The aggregate sizes, should we do coarse and fine as the rubble, the ASR rubble, or whatever else? Then we're looking at the types of water binder ratios that we could use, and also the mixed proportions and the types of supplementary cementitious material. Next slide. So at the moment, sorry, this is not visible. At the moment for the PhD, like I said, we don't have the rubble as yet. So we are in communication with the JRA to to locate where it is so we can get it to use it for our investigation. And we are going to be looking at the durability, the long-term elastic deformation, and the just elastic deformations. So for the durability, we'll look at the chemical mechanisms, which are looking for at sulfate attacks, alkali carbonate reactivity, alkali silica reaction, and corrosion. For physical mechanisms, we're looking, you might consider the freeze flow deterioration and porosity permeability. So with that, then there's water subtivity, chloride induction, and oxygen permeability. For long term, we're looking at creep and shrinkage. And for just elastic testing, we're looking at slump, compression, and sieve, the other tests. So yeah, thank you. I'm done.
Thank you very much. Thank you very much. You almost made it on time in spite of all the difficulties. So we'll take questions.
Okay.
We'll take questions. Any questions, please?
Can I ask a question?
Sure, go ahead, Mark.
Yeah, and the obvious question is, you know, how would one prevent ongoing ASR if you've got concrete that has already been connected to ASR? Dikeledi, what do you think about that?
How would we prevent ongoing ASR?
Yes.
Okay, that's another situation. Okay, so at the basic level, we would have to then, with our cement paste, trying to make it less reactive, or actually having admixtures in so that we kind of reduce the ASR development, I think, from the top of my head at this moment in time, because I haven't done a lot more into that. But I'm thinking either adding something or making sure that what we are mixing our ASR affected aggregate is not actually going to be as reactive.
Have you thought of any gel removal process to get rid of the ASR product, Dikeledi?
No, at this moment, I have not thought of any gel removal process, but I would consider it as I do more research.
Okay. And do you think it would be better to go for the finer aggregates than the coarse aggregates? Do you think there would be better effect if we look where you use only the fine or more of the fine material?
So at this point in time, because there was no actual decision, I could see when I'm looking at the coarser and the larger one, that means we're introducing more gel, and then it could in fact affect the rest of the concrete more easily. And perhaps if we're using but then the proportions are different. So we still have to maneuver around that. So like I said, we haven't really decided or come to the conclusion on whether it should be coarse or fine. And those are the finer details that we're going to have to think about to say, are we actually overloading our structure by using finer aggregate or the other coarser aggregate? So that's something I have to consider.
Sure. There's also a question, or it could be taken as a suggestion of doing something to the concrete to reduce the permeability so that you can reduce the effect of ASR.
Okay.
You could also think about it.
Okay. Yes. Okay. Water. Okay.
And there's also a suggestion about using e-waste.
E-waste?
Yeah, electronic waste. But I think you have enough of problems with the ASR itself before you add waste to the concrete.
Yeah.
All right. So it looks like you have a lot on your hands, and you have, as we see in your last slide, you have many things that you are going to study.
Considered. We're considering. Yes.
Okay. So all the best. Thank you very much. And sorry about the technical problems we had in the beginning.
Sure. Thank you so much. Sorry to everybody.
No
Thank
problem.
you.
Thank you. So those were the two talks that we had in this last session to talk about the way forward and to discuss what we can do further in this project and in this collaboration. I would like to hand over the screen to Professor Hans Boyshausen of the University of Cape Town. Hans?
Yeah, thank you, Ravindra, and good afternoon, everyone. So I'm Hans Boyshausen from the University of Cape Town. I have not prepared a PowerPoint presentation, so you can now opt to look at my face on the screen here or just go to the general view where we can see each other's faces for those who have switched on the camera. So my task is to summarize the discussions, point towards the way forward, and to close the workshop. Now, first of all, I'd like to thank all the presenters. You have once again, you students made us proud. Very well done, great quality of presentations, very good work has been done in the different places. And I must say that COVID has impacted all our lives, but in a way, if I look at this workshop, it has had also some positive impacts. Certainly it has improved the way we deal with technology, how we cooperate internationally, and how we present our work on this level. So I think we should take that one positive effect and acknowledge it. Now, Manu started off the workshop by asking a few key questions. And just to remind you of those, the first one was, how should the performance approach be modified when recycled aggregates are used? And following that is, do we need a different set of limiting values when we do the performance approach? And just to explain that briefly from my perspective, the performance approach, especially for durability, is largely based on measuring durability indicators, such as permeability, diffusion, sorption, and conductivity and all that. And then calibrating that with the actual durability performance, such as ingress of chlorides, carbonation, reinforcement, corrosion. And we've done that for conventional concrete for the last 20, 30 years. So we know that correlation. Now we're using a new type of concrete, so to say, and the change in the microstructure from the recycled aggregate will possibly change the way we calibrate our durability index or indicator methods to the expected performance in the field. So we have to find out how can we best characterize recycled aggregate concrete so that we identify all its benefits and the shortcomings. Okay, following that challenging background key questions, we had 6 presentations. The first one from Ram. He spoke about environmental performance of construction and demolition waste recycling facilities. He clearly indicated the urgency of the problem using the example that India's tallest garbage mountain is nearly as high as the Taj Mahal. So I think that's quite a scary, a scary thought. On the other hand, so we have got so much construction and demolition waste. On the other hand, natural resources for concrete production are quite limited, especially sand, but also, of course, coarse aggregates. And studies clearly show there is enough construction and demolition waste available to supply the industry. There are certain economic challenges with processing recycled aggregates that have to still be overcome. And in terms of sustainability, the presentation has clearly shown that recycled aggregates has much less negative impact compared to natural aggregates, as in fact was expected. Following that, Nirma presented to us on the effect of partial replacement of fine recycled aggregate on concrete durability. Now, in the introduction to the talk, we've listened to all the commonly perceived potential negative effects of fine recycled aggregates on concrete properties, such as loss in workability, loss in strength, higher shrinkage, and so on. And also various enhancement techniques were presented in order to overcome those potential negative effects. However, and I want to point this out in particular, all these potential negative effects, that's how we commonly see our recycled aggregates. We are trying to mitigate problems that we might expect from using recycled aggregates in concrete. Whereas on the other side, there are also potential benefits to be gained from this technology. We have an additional amount of cement paste in the concrete that can cause problems, but also it can give us benefits in terms of technical performance. We have hydrated and unhydrated cement paste. And that in fact might lower the penetrability of the concrete, which Nirma has nicely shown by giving us the information on carbonation, where the recycled aggregate concrete had drastically lower carbonation depth compared to the reference concrete. And this also relates to one of the key questions asked earlier by Manu: how can we characterize this? Because in the same time the oxygen penetrability was not changed positively. So if we were to use the common durability methods, we would not be able to characterize the potentially positive effect that recycled aggregate has on performance, which in this case is carbonation. So with that, I would also like to personally propose another key question. How can we move away from considering construction and demolition rubble as a waste? It is in fact a resource. And at the same time, we need to move away from trying to only mitigate potential negative effects that recycled aggregates can have on concrete properties. And we have to start looking more into the positive effects. That means the technical positive effects that we might be able to achieve with certain methods, and then sell that appropriately to industry. And not only look at sustainability, which is in this case, I think, the lower hanging fruit. Okay, and in this regard, I think Nirma's presentation showed some promising results. The third presentation from Lepocho and Cadimo spoke about the effect of masonry rubble as fine aggregates on concrete properties. So here again, we used construction and demolition waste, but not a concrete, but we crushed down the clay bricks. And what was identified was a strength gain and also a slightly improved durability, especially at higher water binder ratios. And to my mind, there is a potential of a pozzolanic effect that we might want to investigate further to see how we again can improve the concrete properties by using this material and fully understanding what it actually does to the concrete microstructure. The fourth presentation from Rohit looked at thermomechanical treatment for extraction of aggregates from recycled concrete. And so the technology that was proposed aims at removing adhered cement paste and mortar, in fact, from the coarse aggregate fraction. And what was shown was that with increased temperature and increased heating duration, the aggregate properties can be improved and more of the adhered mortar can be removed from the aggregates. Personally, I would question whether at 500 degrees Celsius treatment, we are still talking about a sustainable technology. So I think that needs to be considered. A similar thought was picked up by Ichibadu, who first gave a good overview of all the different common pre-treatments available or tried out or used in industry in order to improve the properties of aggregate. And he also pointed out all the different shortcomings, often related to increased processing times, costs, other aspects of energy use, which again take away the sustainability from the material and so on. His research is in the early stages, and what he's proposing is to look at using pozzolanic slurries in the actual mixing process, which would be quite easy to implement, which wouldn't necessarily add costs or any processing steps, and which may or may not improve the properties of the concrete significantly. So watch this space, and I wish you good luck in your future research. And lastly, we had Dikaledi on durability and deformation properties of ASR rubble concrete. And the question here is, as far as I gathered, how does the inherent deterioration in the recycled aggregate affect the concrete properties? In this particular case, ASR deteriorated concrete. Again, early stages of research. So also for you, good luck in your future PhD. And your first question was, you're not quite sure when the time comes when you stop asking questions and finding new knowledge. I think the time to ask questions will never stop. Throughout your PhD and also subsequently, if you've done a good PhD, then you have discovered more questions than answers. I think that is what makes a good PhD. And now there's the question, where to from now? And I just thought about it, and then I would like to hand over to you guys to ask some questions and contribute to the discussions. I think first of all, we need to start to improving the processing technology for construction and demolition waste to really understand how we can best extract a good resource from that waste to be used in concrete without using too much energy or too many processes that would make this technology potentially unsustainable or uneconomical. Once we've done that, we need to find out how can we improve the properties of recycled aggregate concrete. And in fact, as Manu said, how can we best characterize that? How can we optimize the performance using suitable test methods for us to understand what actually is happening? The positive effects in terms of sustainability are quite obvious, but we still have to find out about durability. What really does this recycled aggregate do to durability? And not just how can we mitigate negative effects, but how can we harvest positive effects? And similar thoughts will be true for mechanical properties. And I believe once we've done all that, the biggest challenge is yet to come, because then we have to convince industry to actually use this new technology. And the construction industry is notoriously conservative and risk averse. So any new material will be met with skepticism. But I mean, maybe legislation and people such as Greta Thunberg and the like can assist us here in driving sustainability, as long as we can show that this technology is also having technical advantages. So that is my summary of the workshop. Thank you very much for your presentation. And Ravindra, I believe you tried to gather questions that can be discussed in this closing session. I don't see anything on my screen. So in the absence of that, can I ask anyone to please indicate if you have any comments or any additional views on the future of recycled aggregate concrete? Yunus Bellam. Yes, please, Yunus.
Okay, thank you. Colleagues, can I say firstly, this was a most fascinating discussion, and I want to echo the point that Hans made, which is our students are really doing some exciting things. The second thing is that I want to go back to Ram's presentation, which was about making a case for recycled aggregate. It may sound obvious to most of us, but I do think that we need to spend time making the case.
Yunus, we're not able to hear you clearly.
Can you hear me now?
A little better.
Is that clearer? Is that clearer?
Yeah, that's clearer, I think.
Okay, I was making an argument that we need to spend the time making the case for the use of recycled aggregate in concrete. It seems obvious to everybody, but I do think that we need to spend the time. And it reminds me of the time when we were in the early years of introducing fly ash into the South African construction industry. The biggest hurdle was variability of the material. And I do think we need to find a way in which to respond to that. And I want to use the parallel a little further. What resolved the problem of variability of the material at that time fly ash in its application and use in concrete was the fact that we went to the source of production of fly ash and said to them, please keep control of the quality of the material. It's not a waste material, it's a resource. That's the point that Hans was making. And I think we're going to have to go to municipalities and take sort of local authorities along with us as we go through this journey. Because separating, classifying construction rubble waste is going to be an important part of our ability to use this material to convince contractors and so on that it is worthy of being used, and then more importantly of specifying. If the material is too variable, we're not going to be able to specify it. And then sort of but I don't think it is impossible. I also make the last comment on that subject. The thing that really swung for us the use of slag and fly ash in concrete was when we demonstrated the superior engineering properties as opposed to plain Portland cement. And that really swung usage, and people started believing this material and taking it more seriously. The last comment I wanted to make is that the material science complexity of rubble aggregate concrete is intellectually interesting to all of us. I mean, I think a number of you have shown, a number of the presentations have shown that we're introducing new complexities in the material.
And it really is intellectually exciting, and I think we should take advantage of that because it does produce new ways of thinking about this material. So I'm looking forward to a lot more exciting work, and I just wanted to add that. So thank you very much.
Okay, thank you very much. I didn't understand all of it, but I think what I heard was very relevant and informative. Also, what you say is we need to look a lot at the engineering properties of the material, because I think those are also the most relevant for many people in industry. We talk to them about durability, but they want to talk about compressive strength because they often don't understand the significance of durability. So we need to look at all those different properties in order to develop this technology further. Prof. Alexander, I see you have unmuted yourself. Does that mean you would like to talk?
If you will permit me, Professor Boyshausen, yes, thank you.
I will.
Thank you. You know, we do good research, no doubt about it. Both of these groups, or all three of these groups, do good research. We can solve these technical problems, I have no doubt. The problem is always, as Professor Ballum has pointed out, the acceptance in the industry and also the regulatory environment. So we really should be forming multidisciplinary teams here and working with the policy people. Prof. Ballum again said the local authorities to bring them on board. And that's our problem, I think, as engineers and as researchers. We work in these silos. And some of the work that we have done showed that these things are quite possible, but it's how to get past those other barriers. That's just a comment. The other thing is, can we not take a leaf out of the asphalt paving industry here? Because the reason why asphalt paving has been so successful in recycling asphalt paving is because they take the pavement up and they simply put it back again in the same place. They don't have to transport it. They don't have to go and get raw material except a little bit more bitumen and so on and so forth. And I mean, it's a high success story. What can we learn from them in this regard? Take a big city like Chennai or Johannesburg. You know, on the regulatory side, could we not be insisting that a building that is demolished has got to be reused within the precincts of that downtown core? It cannot be taken outside of the downtown core. It has to be reused in situ, as it were. Then you also have control over quality and all the rest of it. So I think that this is just a challenge. I'm just throwing out some ideas here, that the problem is actually much bigger than just a technical one, which I'm sure we're going to be able to solve those issues. Thank you.
Thank you. Yeah, I fully agree with that. I think we have to always look at the bigger problem, and we also always have to be realistic. And I've seen lots of research on recycled aggregate concrete, also recent research, not in India or South Africa, but in many other parts of the world, which is sometimes a bit esoteric or very scientific. And I think the moment we lose sight of what will be acceptable or doable in practice from all the different viewpoints of the construction industry, then we start losing the plot. So I think very important that we keep all this in mind when we do our research. Manu, I also see that you are unmuted, so I would invite you to talk.
Okay, thanks, Hans. Just wanted to add, I think Professor Ballum had mentioned that policy is very important with respect to how we get about using this material. And we can take a leaf out of what we've learned with the fly ash experience. I think with fly ash, it took a long time for people to get going because I think they did not realize for a long time that this material is actually harmful for us. That means if it is left lying around in the ponds and everything. So with recycled aggregate, I think this kind of sensitization has to happen much quicker. And as again, Mark also was mentioning, if we come up with good policy decisions that demolition waste cannot be taken out of a central core zone and it has to be reused, then definitely I think there will be some ways in which we can solve the technical problems to get these things into the practice. I think a lot of our experience from the cities where recycling is actually happening also seems to suggest the same. I think, for example, if you take the example of Bangalore, they have good recycling concrete facility available. However, there's not much enthusiasm on the parts of contractors to use recycled material because they can actually get cheaper material from the natural source. So there is nothing really that is pushing them to use it. And if only we can actually show the way in terms of utilizing this material and not just focus on the sustainability, as you rightly said, but also on the positive mechanical and durability properties that can be brought about. I think there's a lot of work to be done in that regard.
Thank you. I agree. There was an interesting comment in the chat also that the challenge will be in the consistency of production of recycled concrete aggregates, and also testing and quality control will be the key. So yeah, we need to find a way how we can get consistent quality from this material to produce concrete with consistent quality, and have test methods with which we can characterize the concrete accordingly. We have another 2 minutes or 3 minutes left. Is there anyone who would like to say a few last words? Ravindra, a last word of wisdom from you?
Well, what I could do is, as Mark and Hans also know, there is this Global Cement and Concrete Association Consortium, and they have identified 15 hot topics to do research on. And 2 of those were related to recycled concrete. One was to look at life cycle costs and life cycle carbon footprint of different ways to extract aggregates from old concrete. And that is something that I also saw in the questions that were put on YouTube. People were asking about cost and which way to process would be better. So that is something I think we could start looking at. Ram's research pointed a lot in the directions that we should move. Then the other area that GCCA has looked at are the very fine material coming out of the recycling, so that we don't dump like we used to do with fly ash, or we still do with fly ash. So the recycling will come up with a lot of very fine material. So the question would be, what do we do with that? Can it go back into concrete? Can it go into cement? Can it be used as the raw meal for cement production? So this is input that can drive further research and point our students to some areas that we could be working on. Otherwise, I enjoyed the workshop. I'd like to thank all of you for putting this together. It was wonderful. And I think it's great to see the students, the next generation or the youngest of the researchers, to step up and do such a marvelous job. So at least from my side, I don't have to worry about organizing conferences anymore. They are good people, good young people who can do it. And to see the network across 2 continents and to have so many people from different parts of the world join was very thrilling, very promising, and great job to everyone.
Okay, thank you very much, Ravindra. Very nice closing words from you. Yeah, I must say that this topic of recycled aggregate is certainly a hot topic all over the world, and our cooperation that we have established between India and South Africa is certainly on the right track. This workshop, we have identified a lot of research needs and opportunities, so we have something to think about when we go home now. Well, we are home, so once we switch off the computer. And cutting edge research, I think we are there. We can't see each other at the moment in person, which we had planned with this cooperation. But I think what we've done today is a very good example of what can be done with Zoom meetings and the like. So in terms of this research cooperation, India, South Africa, watch this space. There's a lot to come. Thank you very much for your attention, and I look forward to the next workshop. Bye-bye.
Bye-bye.